one of his specializations is doing these fantastic scientific visualizations. So he will tell you a little bit more about the truth and beauty parts of that and what has inspired him to create these during his talk. So enjoy.
All right. Can we get the lights down? Is Keely here?
Yeah, I'll go with it.
Hey, Keely, can we get the lights up? There we go. Beautiful.
Is that too much?
No, that's beautiful because we do astronomy and we have a lot of black, so we got to have the lights down in the room in order to really work. All right, so thank you very much, Bonnie. Bonnie is another astronomer in the Office of Public Outreach at the Space Telescope Science Institute in Baltimore. And as you might guess, the title of my talk reflects the most famous lines from this gentleman, John Keats, who I found out lived only to be 25 years old. All right? But when he was age 22, he wrote his most famous poem, which was Ode on a Grecian Urn. And I have here just the last stanza of Ode on a Grecian Urn, and it's really the last two lines where the urn is saying, "To whom thou sayest, beauty is truth, truth beauty, that is all ye know on earth, and all ye need to know." Now, that is a line that equivalences truth and beauty and puts it up on such a pedestal. And the public actually became very enamored of it. They liked this idea that truth and beauty could somehow be equivalent. Of course, if the public likes it, you know that the critics are going to hate it. So, Josiah Condor in the Eclectic Review said, "That is all that Mr. Keats knows or cares to know, but till he knows much more than this, he will never write verses fit to live." Of course, Keats' verses, especially the lines he's criticizing, did live, and the only thing that I've ever heard of Josiah Condor, of his words that lived, were his criticism of Keats. However, T.S. Eliot said, "On rereading the whole ode, this line strikes me as a serious blemish on a beautiful poem. And the reason must be either that I fail to understand it, or that it is a statement which is untrue." And when you've been dissed by T.S. Eliot, you've been seriously dissed, right? Well, I'm not an English major, and this line has never really bothered me because this is a line where the urn is supposed to be speaking to man and saying that beauty is the highest goal. And the urn is a piece of art. And in art, attaining beauty is your highest goal, so beauty can be your truth. All right? And your truth can be beauty when you are thinking in art. So it's never really bothered me. Of course, I'm a scientist. And in science, we're trying to get at the truth, or at least a good approximation thereof. And we also have an idea of scientific beauty. This is the Institute for Advanced Study in Princeton, New Jersey. Very famous think place for deep thinkers. And the IAS medal actually pulls from Keats and has truth and beauty. Or when I was in Princeton, we called them Ruth and Betty. And you can see that the IAS is dedicated to uncovering the naked truth. Now, they specifically quote Keats when they're presenting this because scientists are in their quest for truth, really do see beauty. And the example I'm going to give you is the most famous resident of a person who worked at the Institute for Advanced Study, Albert Einstein. When he came over to America, the IAS in Princeton is where he did his research. And Einstein's theory of general relativity, which he's writing on the blackboard here, the fundamental equation of that is that the Ricci tensor is equal to 0. You set the Ricci tensor equal to 0, and you can get out the equations of general relativity. And this is an amazingly beautiful theory, okay? Because it takes the forces of Newton's gravity and replaces them with space-time curvature. So instead of a force pulling on Earth and keeping it in orbit around the sun, instead the space-time around the sun is curved and warped, and that curvature and warp produces the orbit of Earth around the sun. And all of that wonderful idea of space-time curvature can be expressed by a mathematical equation, a tensor equation, given here. And it is very symmetric. It's symmetric in space and time. All right, these Greek subscripts here, mu and nu, actually cover both the space part of it and the time part of it. And to be able to take space and time and work them together is a very beautiful symmetry. However, I will be honest with you that the Ricci tensor here is actually defined in terms of partial differential of something called the Christoffel symbol. And the Christoffel symbol is also defined as partial differential equations of the metric tensor components. And so, actually, we usually called the Christoffel symbols in graduate school the Christ-awful symbols, because when you had to try and solve these equations, it was really an awful lot of work. So I must say, at least for me, getting into the really depth of the mathematics here removes some of the beauty from general relativity, but I can still appreciate its wonderful, the wonderful symmetry that it has. Now, I'm from the Space Telescope Science Institute. We're the science home of the Hubble Space Telescope. So we got it easy. We don't have to start with truth and try to lead you into understanding the beauty of these equations. We got the beauty right in front of you, okay? We've got the amazing images from Hubble of planets and of stars and of nebulae, amazing views here. We've got galaxies, and the images from the Hubble Space Telescope, using them, we can start with the visual beauty of the universe and use that to sort of lead you in to the scientific truth. And so that's what we do in the Office of Public Outreach. We're able to take the amazing images from Hubble and bring it out and teach the public about astronomy, using them as a drawing in card to then get you into the science. So I'm going to tell you a few stories tonight. And I have to thank my collaborators, Greg Bacon, Lisa Furtari, and Zolt LeVay. These are my three main collaborators on a lot of the work you're going to see tonight, as well as Tiffany Davis up here, who's no longer with us at Space Telescope. She's still alive. She helped us on some of our projects here, okay? All right, 4 stories for you. I got so much to tell you. I'm going to have to really zoom through it, but here we go. First, we're going to start with Night of 1,000 Stars. So when you look up at the night sky, well, you can see lots of stars. You really can see thousands of stars. Actually, across the entire celestial sphere, the human eye can see about 6,000 stars. Now, people might recognize the familiar pattern on here. Who knows what that is? Just shout it out. Orion. Thank you very much. Got to make sure that everybody catches that. And this bright star down here is Sirius. And up here we have the Pleiades and Taurus in Taurus. All right? So we have these constellation patterns in the sky, but we have a big problem in astronomy in that we draw on these wonderful little stick figures, okay? We draw these 2-dimensional stick figures, all right? And you make it look like, okay, all these stars are, you know, like a connect the dots on the sky. And then to further, we actually draw in, you know, the mythical ideal of Orion. This is Hevelius's constellation. You can see the stars of Orion's belt, all right, and Betelgeuse, which some people say actually means armpit of the giant, okay? And he's got his shield up here facing Taurus the bull. Sirius is part of Canis Major, which is his hunting dogs. And then we can actually, you know, take this fanciful interpretation of the night sky and we turn it into celestial spheres. So here, for example, is a wonderful celestial sphere at the Woodrow Wilson Memorial in Geneva, Switzerland, with all the constellations drawn on a sphere. All right, all right, and we use this not just as art, but we also use it as teaching. We have these celestial spheres that we use in order to teach the night sky. Now, in the celestial sphere, of course, Earth is at the center, because we're looking at the inside of a sphere from Earth, and when we teach with it, we draw things on the outside of the sphere, because we're looking in. The problem with this is that it exacerbates the concept that the stars are 2-dimensional patterns in the sky. All right? When you look at this, the naive interpretation is all the stars are at the same distance. And that can lead to some serious problems, not just in art, but also at some places that you might know about. In particular, Grand Central Station in New York City. when they did the sealing of Grand Central Station, they wanted to put the night sky up there. They went to a book and got the constellation drawings, but the constellation drawings were for a celestial sphere, which was the outside of the sphere. All right, and so they put them up on the inside of Grand Central Station, and if I zoom in, you can see that Taurus is not up to the right of Orion, it's up to the left of Orion, and the constellations are backwards on the ceiling of Grand Central Station. Except, you will notice that the stars of Orion actually look correct, because it appears the artist knew what Orion looked like, and knew that what was drawn wasn't right. If he had done it correctly with the celestial sphere, it would have looked like this, with the stars going up to the left, and here they are going up to the right, and instead of Betelgeuse and Rigel being here, they would have been on the other side. So when you go to, next time you go to Grand Central Station, you can look up and you can go, wait a minute, those constellations are wrong, except for Orion, and you can laugh and everyone else will look at you funny, okay? But for one of our educational things, we wanted to combat this idea that a basic misconception that stars are at the same distances. So we're going to visualize the stars. How do we start? We got to start with the scientific data. And the scientific data in this case is the Hipparcos catalog. Hipparcos is a satellite that surveyed stars. It has a catalog of over 118,000 stars, where it gives you the positions on the sky. And the most important thing is it gives you the parallax. Okay, that's a measure from which we can deduce its distance. So not just the 2D position on the sky, we can actually get its third dimension and distance. It also gives us the spectral type of the star, which I'll show you in a minute how we get the color from that, as well as a measure of its brightness, which we astronomers call magnitude. Okay? One problem with Hipparcos is that it was a satellite trying to survey the whole sky, and the catalog selection was more for getting basically even sky coverage across the whole sky, and not really a completeness in a scientific sense. So we augment that with the Yale Bright Star catalog, which is meant to be just the brightest stars in the sky. And this has 9,000 stars with the same information available, and it's roughly complete to about 7th magnitude, which is a measure the human eye can see down to about 6th magnitude. This goes a little bit deeper than the human eye can see, and this fills out the completeness of the brighter stars for us for our star catalog. All right, so here is that image I showed you before of Orion, and I want to recreate this in a visualization. All right, well, we actually have a lot of really bright, large range of stars here, from the brightest star in the night sky, Sirius, all the way down through some faint stars, and I can pull those out and show you an idea of what they look like. So here are the stars with magnitudes from 5.67 all the way up through magnitude minus 1.46. So if you're not an astronomer, the astronomy magnitudes actually are an inverted scale. Okay, lower is brighter. It's better to be a star of the first magnitude instead of a star of the second magnitude. And so you can see that as you go through this top line, you can see you get a nice core that brightens up. But once you get down here into the brighter stars, you can start to see there's some fuzz around here. We astronomers call those wings. All right, so there's a wings that spread out from the star. So as the star brightens, all right, it builds a core, and then it builds wings around that. And we need to reproduce that in visualization. Well, visually, we tried two different functions. One, which is a Gaussian here, and the Gaussian produced that nice core, as you can see as we get to brighter Gaussians, but it didn't have much in terms of the wings. So we tried the exponential function, and the exponential function produced some nice wings, but it's got a relatively tiny core. So the answer was, of course, to combine the two, work together, combine the Gaussian and the exponential, and here are the visualized stars where you can see from the faint stars, they brighten up, get a nice big core, and then they slowly build up some really big wings. All right, but you'll notice here that these are all the same color. Now I have to burst your bubble, okay? What color is the sun?
Yellow.
Thank you. Most people think the sun is yellow. We draw it as yellow. It appears on our art as yellow. The sun is not yellow, okay? The sun, when you look at its spectrum, actually peaks in the green. All right, the peak of the sun spectrum is in green, but when you combine the sun spectrum with the red, green, and blue cones in your eye, the sun is actually this color. Now that looks an awful lot like a black and white image, but I tell you it's just slightly tinged in terms of sort of peachy color. All right? We think the sun is yellow because when the sun is setting and the sky gets orange and red, the sun looks yellow down there, all right, because of all the blue light that gets scattered out of the sun's rays when you're looking at it at sunset. But if you really look at the sun and measure it, it's more like this. And especially if you get above Earth's atmosphere where there's no interference, the sun will look like this. So if you take all the stars and you compare their colors, you get something like this. So astronomers, the spectral types, O, B, A, F, G, K, M, which while I was a graduate student at Berkeley stood for, oh boy, Alex Filipenko gives killer midterms. That's how you memorized the astronomy types. You may have something different here at UT. And you can see that it goes from these blues through some whites and some peachy things to some orangish reddish things. And this right here, this is the calculated color of the sun for this. So using this, we can then add those colors in to our database. So we've got the stars, we've got their 3D positions, we've got the way to approximate their magnitudes with the Gaussian exponential, we've got their colors, and that produces this. On the left is the image from Akira Fujii, and on the right is our visualization of it. All right, and I think we do a reasonable job of reproducing what the stars look like. Now you may say, well, that's fine because you've got the reference image. But what's really cool about this is that we now have a fully three-dimensional view of these, and as the camera moves away, we will keep the proper view of these stars. All right, because this is all 3 dimensions, and so the brightness of a star is due not to its intrinsic brightness, but also the distance it is from where you are. All right, so we can take this visualization, all right, and show off and break through some of those misconceptions. So here we are just panning across the sky. We've got Procyon and Sirius, and here we have Orion. Now we're going to draw in the stick figure of that constellation, and then we're going to break it. We're going to start to circle around the Orion constellation. And you can see very quickly that ain't no 2D constellation. It is so big, matter of fact, that we actually have to back the camera up in order to keep it all on screen. Now we continue, and we're going to make a full circle around the constellation of Orion. And in working with teachers and students on this, you can see how this very quickly just blows your notion that the night sky is a 2-dimensional object, that the stars are all at the same distance. Some kids have said, oh, that looks like a stealth bomber constellation in 3 dimensions. Now the other thing was that the idea that if you look from the outside, you'd see the reverse of Orion. And I'm going to pause it right here. Whoops, I quite missed it. This is sort of the back side of Orion, if you went around the exact opposite side. Does it look anything like Orion? No. You go to the back side of Orion, and it looks different because of 3-dimensional perspective, but also because you see this star here, that's the brightest star in the constellation right now. All right? That's Alnilam, which is the center star of the belt, and it's the most distant star, whereas Betelgeuse is now relatively bland compared to Alnilam. The brightnesses of the stars would totally change because of the distance away. So now that we're located on the opposite side, the most distant star then becomes the brightest star. All right, I will continue this. You'll also notice the dearth of stars over here, because this constellation is so stretched, we actually get to the edge of the data sets that we put into this visualization. So you can see a lot more stars closer to the sun, which is, of course, what you would expect for a survey done from the solar system. All right, so that brightness is really well illustrated at the end of this visualization, because we're going to come back to the Earth-Sun axis. But remember, we pulled back in order to get this circle to work. All right, and so now we get here, we sort of get something that looks like Orion, but where's Sirius? There's supposed to be a bright star down here. All right, Sirius isn't there. Well, it actually is, but watch that bright star that appears right there. That's Sirius, the brightest star in the night sky. And as you can tell, once we pull back, it didn't look so bright. The reason it's the brightest star in the night sky is not because it's an intrinsically really, really bright star, but it's a reasonably bright star that also happens to be pretty darn close. So there you go. You get the stars in the night sky. Let's go one step further. All right. For one of our visualizations, we use something that I call synthetic stars. All right, and we analyzed a Hubble image, and we created a star database of the stars in that image, position, brightness, and color. And we know what we call the HST point spread function. I talked about that Gaussian and the exponential that we use to see how a star grows. Well, we measured that for the Hubble Space Telescope, and we call it the point spread function. All right, and we can take this press release image and try and recreate it with a synthetic set of stars. So here is the image we're going to try to recreate. All right, and so we run a piece of software called Source Extractor on this, identify all the stars, identify their brightnesses and their colors and their positions on here, and then synthetically, from that catalog, try to recreate this image. So here's the real image, there's the synthetic image. Real image, synthetic image. And you might say, okay, that's kind of cool, but now that we have that, we can then pull that out into 3 dimensions, or we can do some really other cool illustration things. All right, so this visualization here takes that image and concentrates on a small section of it. So we're going to zoom in on that. Uh-oh, my laptop's not having fun with this movie. It played perfectly the other day. Okay, now let's separate these stars according to their brightnesses. Since they're all synthetic stars, we can move them as if they were on a plot. All right, we got the blue stars on the left and the red stars on the right. But now let's separate them according to their brightnesses. Let's take the bright stars to the top and the faint stars to the bottom. And what do you get? You get the canonical diagram of stars called the Hertzsprung-Russell diagram, taught in every astronomy course. But you do it using the actual stars from the image. And you will see that what we call this is the main sequence. Most stars fall along this track in the color versus brightness diagram. They fall on a thin sequence called the main sequence. We get the red giant branch, stars that are cool and red but huge, so they have a huge luminosity. We have over these here the white dwarf strip. We can take the image, an actual image, work with the stars, and show you how the Hertzsprung-Russell diagram pulls out of that naturally. Kind of cool, especially to us geeks. All right. Let's go on to the next topic. The next topic is galaxy collisions, and we'll talk about something I call a smash hit. So make sure everybody knows what a galaxy is. A galaxy looks like this. This is one of our Messier 101. It's got these giant pinwheel arms, and it's composed of hundreds of billions of stars, along with, you see, these dark dust lanes of huge clouds of gas and dust. And these spirals are the prettiest ones. My favorite actually is this one, the Whirlpool Galaxy. Amazing image from Hubble with beautiful spiral arms and these wonderful star-forming regions, these red splotches in here. You'll also notice that M51, the Whirlpool, has a companion. And that happens a reasonable amount of times for galaxies. Galaxies actually do pass by each other, and they form in groups and clusters. Here are 2 galaxies that are just passing by each other. They're not interacting with each other. But when they do interact, they can rip each other apart. They can take those beautiful spiral disks, rip them apart, and go create these amazing shapes. Galaxy interactions, galaxy collisions to create amazing distortions to the galaxy shapes. So, we want to simulate this. Well, let's start with the idea of the n-body simulations that we do for research. Simple idea that we've got one particle here and a second particle here, and they have mass m1 and m2. They're located at a distance r apart. And then we can calculate the forces between these two particles, the gravitational force, and that's simply Newton's equation. The force is the gravitational constant, proportional to the masses and inversely proportional to the square of the distance. And that we can do via pencil and paper. You will do it in your physics courses if you take them. But that's simple for two particles, but what if you've got, say, hundreds of particles, or millions of particles, or billions of particles that we are now doing in places like the Advanced Computing Center here on the campus? Well, then you need a computer to calculate all those forces for you. And you can take that computer, take all the positions of the particles, calculate the forces, move those particles, calculate the forces again, move them again, calculate, move, and so on. That is what we call an n-body simulation, all right? And these n-body simulations, we use particle-based gravity, all right? So it calculates the gravity between all these particles to see how they move. However, that works fine if you're talking about point masses like stars. If, however, you take gas clouds actually have a volume around them, and if they smash together, well, then they heat up and shock and they combine, all right? They actually get denser. And so we use something called smooth particle hydrodynamics to represent those gas clouds, and they actually have a density profile. They actually have a size, and they're denser in the center, and their density falls off. And so, you know, you can do both gas and gravity, like with this. All right, so here is a plot of particles in a n-body and SPH simulation. Here are the stars down bottom, and here is the gas up top. However, this is just putting a simple point where every particle is. And it doesn't take into account that these points actually are clouds that have a density profile. So when we wanted to visualize it, we said if we do this, it looks nice, but it doesn't really capture what's truly going on in the simulation. What's truly going on is, well, you've got this smoothing kernel or this density profile, and if you take that three-dimensional density profile and you compress it, you project it onto a 2D plane, you're going to get a 2D profile to work with. And we can represent that by what we call a splat, okay? Just like that Gaussian splat of light that we use for the stars. Well, it turns out that the 2D profile is this solid line here, and if I plotted a Gaussian on top of it, you can see, except for way out here in the tail, the Gaussian is a really good representation for it. So that same Gaussian that I talked about using for the stars, I can also use for the SPH shader. But what's important with the SPH shader is that as the gas cloud gets into a dense region, it gets smaller, okay? Or if it's in an empty region, it's much larger. So it changes its size over a course of space and a course of time. So instead of, that's just for the geeks in the audience, all right, instead of having just dots here, we then replace it by this SPH shader, and you get that. You start to see the structures much more detailed because your visualization method is geared to what's actually going on in the simulation. And it's not just the gas. The stars also have a small density profile by the gravitational softening length, and the stars also show structures that you wouldn't see otherwise if you were just doing simple dot-to-dot plotting, as we call it. Combine those and your galaxies start to look like galaxies in this visualization. Put this together, we have a movie of a galaxy collision, a simulation. This one has a header on it because I didn't have the one without the header on it. I apologize. Okay, so this is the galaxy collision. The simulation was done by Lars Hernquist, who's up at Harvard University, and Chris Mijos at Case Western. And you get one galaxy that just comes right in and buzzsaws through the other, and those beautiful spiral structures are relatively quickly destroyed. And I say quickly, that's on an astronomy time scale, because the time scale of this whole simulation is about 1.5 billion years. So take the whole 1 minute of this visualization, you're seeing 1.5 billion years of time. You can see that the cores of them come back together and merge together. The two galaxies, central things merge, but these long tidal tails will actually take several billion more years to merge together. So that's our solution for visualizing galaxies. But we can take it one step further by taking a trip along what we call the Tomb Ray sequence. Now, the two brothers, the Tomb Ray brothers, looked at galaxies in collision. Matter of fact, they looked at a whole bunch of them in collision, and they decided that the presence of the closeness of the two centers told you something about the age of this collision. All right? And they created something called the Tomb Ray sequence, scientific understanding of how galaxies collide. Now, we at Hubble have a much greater diversity. This is, 2/3 of their set that they had to study. We've got a much greater diversity, and in one press release, we released 59 images of interacting galaxies. And for this, we wanted to be able to illustrate the process of galaxy collisions and show you the Tomb Ray sequence. So, if we zoom in, you can see that there are galaxies at all sorts of stages of interacting. Ones that are approaching, ones that have interacted, ones that are merging together. So here are 4 where you can see in the upper left, they look like they're just coming together. Then the upper right, they're smashing through. Here's one where the tidal tails have developed. And here's one where those centers are coming back together. Place these in time. And I pulled these out of these 59 things, and I wanted to illustrate them with that galaxy collision that I just showed you. So I wrote a program working in some code S2plot to be able to take that simulation, move it around, and look at it from various angles to try and find times in the simulation and viewpoints that would match the images from Hubble. And I was successful in that here are the times in the simulation from what you just saw that match it, and if I spin those around, all right, they will end up matching reasonably well the images from the movie. Then the images from Hubble. Then I can recolor them, and we end up with something that can match this. And we can give you this visualization that takes those galaxy collisions and compares the simulation to the Hubble observations. So here's the time moving forward, and we pause it here and show you how at this stage of the galaxy collision, it looks like that Hubble image. Turn time on, same simulation, and again that galaxy slices through the other. But if you pause it here and then spin it to look at it from a different angle, you can see how we match that Hubble image. Again, turn time back on. The tidal tails develop really quickly, as seen in this Hubble image. And then the centers of the two galaxies know where each other is, and they start coming back together. Spin this around to look at it from a skew angle. You match what you see in that Hubble image. Finally, when the cores come smashing together and mix up all over the place, all right, we astronomers call this a train wreck galaxy, and you view that from this sideways angle, you see what you see in this Hubble image. So this surprised me. I didn't expect to be able to match 5 different Hubble images with just one computer simulation to show off that each image that Hubble creates is just one step, one snapshot in a 1.5 billion year long collision history. Kind of cool. All right. Oops, sorry. Wrong one. There we go. Let's take it up a notch. Let's go from galaxies to galaxies across the universe. And in talking about galaxies across the universe, this is the first of our major things from Hubble. It's called the Hubble Deep Field. This image, when it came out in 1996, saw 3,000 galaxies at greater distances across the universe than any image had ever seen. And we put a new camera on Hubble in 2003, so in 2004, we came up with the Hubble Ultra Deep Field. Not the deep field, the ultra deep field, in which we found 10,000 galaxies, and again, the deepest image of the universe at that time. Looking inside the Hubble Ultra Deep Field, we can see some big galaxies that are relatively nearby, some medium-sized galaxies that are further away, and some small flotsam and jetsam, really distant galaxies that are far away. And you might want to think to yourself, well, what are the most distant galaxies we see in the Hubble Ultra Deep Field? Well, they're actually tiny red dots. And these are really important red dots, okay? Let me explain to you how important these red dots are. One, first of all, they're tiny because they're really, really far away, okay? But also because they're seen when these galaxies were very young. The light from these galaxies has taken up to 10 billion years to cross space, okay? These are redshift 5, redshift 6, so they're about 10 billion light years away. That means the light takes 10 billion years to cross the intervening space before we see it. It left these galaxies 10 billion years ago when they were very young. Now, 100 million years is nothing to a galaxy, okay? Our sun takes 250 million years to just orbit once in our galaxy. But a billion years, a few billion years, 10 billion years, that's some serious time for a galaxy. So these galaxies are seen as they were when they were, children, or correspondingly to an adult, okay? These are young galaxies, so their structure is still developing. And they are red because as that light is traveling across the intervening space, the universe is expanding. And light traveling across expanding universe, the light gets stretched along with the expansion of the universe. So light that might have started out as blue light becomes longer wavelength, and we observe it as red light because red is the longer wavelength end of the visible spectrum. We call this effect redshift. All right. Matter of fact, the light that we see here is actually seen in the infrared, and it probably started out in the ultraviolet. All right. Ultraviolet light that has been stretched by the expansion of the universe to be seen in the infrared, which is why these are small red dots. But the point is that when we look out into space and we look back into time, we can actually piece together the idea of galaxies changing over time, the evolution, the development of these galaxies. So here are galaxies out to 3 billion years ago, 3 billion light years away, and you can see they look like relatively normal galaxies. 3 to 7 billion years away and 3 to 7 billion years ago, well, their structure's sort of ratty. But 7 to 10 billion years ago, you're seeing the structures go down, and you can see the younger galaxies. You can visually see the development of the galaxies. And that's the cool story we want to be able to tell. That galaxies, as we look out into space and back into time, we can see the history of galaxy development. How are we going to do that? Well, we're going to take that Hubble Ultra Deep Field, all right, and we're going to cut out all the individual galaxies. Just like that source extractor program that I talked about for cutting out all the stars, we're going to identify all the galaxies in the Hubble Ultra Deep Field. Furthermore, the Hubble Ultra Deep Field is actually, whoops, I'm supposed to have another slide there. Whoops, I'm sorry. All right, the Hubble Ultra Deep Field is actually part of the Great Observatory's Origins Deep Survey, so we're able to get much more than that. We do galaxies, both the Ultra Deep Field and the Goods Field. We get about 16,000 galaxies. All right, and they come out as these cutouts here. But you can see this is the galaxy we're interested in, and there are other galaxies, of course, in that cutout. We then use something called the segmentation map that comes out of our software to identify, these are the pixels that we want for this galaxy. The rest of them, we can ignore those. All right, we pull those out, and we've got our isolated galaxy. We then take that isolated galaxy, and you can see that this is scientific data. All right, there's some noise there, which if we're making a film, we really don't want that ugly noise around these galaxies, so we have a cleaning algorithm to suppress it. All right, which is easy for these large galaxies, but as you get to smaller galaxies, well, the signal of the galaxy compared to the noise, we have to design a different function for those. And then the tiniest galaxies, you can see that the noise and the galaxy are almost of the same level, so we had to create a third separate function for the really faint galaxies to be able to clean them out and get them isolated so the individual galaxies would be able to float in 3 dimensions. All right, so we've got the images and the image source data, pull that to get the galaxy individual images. We've got this redshift data, we measure from separate data, we've got redshift measurements for each of the galaxies, and that redshift measurement actually gives us an estimate of the distance for that galaxy. Pull that together, we get the galaxy data. The galaxy data and the images together, we can do some 3D modeling, and then we put into our three-dimensional program, which is the same software that Hollywood uses, except Hollywood does all of the three-dimensional modeling within their program. Here, as scientists, we're taking and we're putting everything into 3 dimensions before we bring it in. We read it into the program, and here's the virtual camera, and here are our 16,000 galaxies. All right, they are, of course, just rectangular representations of the cutouts instead of the galaxies themselves. And if I look at it from the side, I wonder what that is. Here's the camera, and we have this great big pyramid of the galaxies along this long, thin line of the Hubble Ultra Deep Field and the Great Observatory's Origins Deep Survey. But if we've done our 3D modeling outside of this program, why do we even need this? Because they got the cool tools for doing camera motions. All right, and we made this into an IMAX short film. And let me tell you, when you're doing IMAX, you gotta move the camera carefully, otherwise the audience is gonna lose their lunch. All right, so getting the camera choreography, here is, for example, the camera moving along the virtual path through the data set to be able to pull it out. And here's where I have to take my microphone down. All right, so this is an IMAX short film. Hold on, there we go. So taking that galaxies across space and time idea and putting it together into a, whoops. There we go.
Galaxies are like islands in a sea of space. They glow with the light of billions of suns. The Hubble telescope reveals nearby galaxies in exquisite detail. Galaxies like these fill the universe. Looking deep into space, we see an astonishing array of distant galaxies. It takes billions of years for their light to reach us. We see them not as they are, but as they once were. In one tiny region of the sky, Hubble finds some 30,000 galaxies. Within a single image, we can explore 10 billion years of cosmic history. Relatively nearby galaxies are fully formed, with complete spiral structures and smooth elliptical shapes. As we travel farther into space, we see galaxies as they were, further back in time. These galaxies appear somewhat disheveled, their mature structures still developing. When the universe was young, newly formed galactic disks were ablaze with star formation. Beyond this point, clumps of stars that are beginning to form galaxies. We've seen but a handful of the billions of galaxies stretched across space and time. Just one small sliver of the universe, observed by Hubble.
All right, we're proud to say that that film won the Large Format Cinema Association's IMAX Best Short Film in 2004. Okay, one last story for you, into the Orion Nebula. All right, so this is that Orion constellation we started out the talk with. And we're not going to talk about the stars. We're going to instead talk about this region right in there. This is the Great Nebula in Orion. And Hubble's view of this very central region, the central region in here in 1995 was this. Okay? Zooming in, you can see the bright stars called the trapezium in the center of the nebula, and going in even closer into that Hubble image, you can see the 4 bright stars that form the trapezium. And these are the hottest and biggest stars in the Orion Nebula. Now, what you also see in this Hubble image are these strange things that look sort of like tadpoles. There are several of them all around, and you'll notice that their tails are pointed away from the biggest star. This star here, Theta Orionis 1c. So there are all these interesting little tadpole-shaped objects, and what are they? Well, these are stars in formation within the Orion Nebula, whose gas around them is being smashed into by the stellar wind from Theta 1c. You know that our sun produces a solar wind, and that solar wind sweeps across Earth's magnetic field, and the charged particles hit our poles, and we produce the aurora borealis and aurora australis. Well, the sun's solar wind is relatively gentle. These giant stars have incredible stellar winds that blow across interstellar space and actually ablate the material. And you can see how these are very bright on the near side, where the intense energy from these stars is smashing into this material. And some astronomers are questioning whether this actually affects the star and the solar system that's forming inside it. Because we know that planetary systems are forming because further away we see these dark disks. That's a disk of material around a forming star. Here you can see one where the star is just beginning to peek out, and here you can see the star is definitely turned on at the center of that disk. This is a newborn star with a disk of material around it, in which within that disk planets are forming. We're seeing solar systems in formation in the Orion Nebula. And for the press release we did for this, we worked with the San Diego Supercomputing Center to create a visualization going into the Orion Nebula to show off what's going on in there. So here you can see the bright stars of the trapezium, as well as these proplyds around them, pointing towards the brightest star. And to illustrate what was going on inside these proplyds, these protoplanetary disks, we added animation to this one proplyd, showing the wind blowing across it, but then peeled back that wind to show the disk in which planets are forming and the jets that are actually generally spewed off by these newly formed stars. Now, this was an animation that was done by, as I said, by the San Diego Supercomputing Center. They actually worked with the Hayden Planetarium. It was in the opening show of the Rose Center for Earth and Space. But we were approached to do the IMAX film Hubble 3D. And we showed the producers the various ideas that we had for doing things, and they loved the Orion Nebula, but they said, can we do it better? Furthermore, could we use that brand new Hubble image in 2006 of the Orion Nebula that looked like that? And we said, sure, we can do this. This will be fun. Well, it turned out to be about 9 months worth of work, but it was really cool. All right, so first thing we got to do is we got to take that Orion Nebula and we got to get rid of those foreground stars because those aren't part of the nebula. All right, so we go to our fantastic image processors and they go poof. They can get rid of those stars. All right, it's not just a poof, but you know, I like to be able to show it like that. The other thing that we have to do is, you see this blue gas in here? Well, that's actually not part of the nebula per se. It's actually some gas that's in front of it. We astronomers call it Orion's veil. All right, and so we have to separate out that blue gas and then erase it from the image and pull it out of the image and fill in where we can't see, and so until we get a vision of just the nebula. However, this nebula image is a nice square, and this is Hubble 3D. We got to get these things floating in 3 dimensions. All right, we can't put a square in 3 dimensions, so we take this Hubble image, we put it on top of a ground-based image from Robert Gendler. We then match exposures and fade and cross and smooth together, and now we have a nebula that we can float in 3D. But again, this is still just a 2D image. We now have to analyze what it really would look like in 3 dimensions. So we talk to the experts, use scientific intuition and scientific knowledge as we've got it to figure out, okay, well, the trapezium, these stars eat out a cave. So there's a cave underneath this dark bar, and there's a valley of material here. There's a ridge along here. There's a high valley along here. There's another ridge along here and sort of a plateau up here. And we use all this terminology to help us imagine what it's going to be like. But then, of course, we've got to go into our software and carve it. And so this is what it looks like in our 3D modeling program. And it's supposed to look like what Hubble sees, because it's the view from Earth. But as we move the camera down onto the nebula, you can see here's the blue gas of the Orion's veil, and that is just a simple geometric sheet, rumpled sheet with the texture of the veil thrown on it. And then if we move down here, you can see the carving that we did of this cave back in here, the infill that we had to do with all the imagery, because of course, no one really knows what it looks like in there. We had to extrapolate from what Hubble sees to what we couldn't see, knowing that there was a cave in there. All right, and then fill in and create the geometry for this valley. This is, of course, still just a 2-dimensional mesh that we have pushed and pulled and shaped and filled in. And a nebula isn't a hard surface, okay? So this is the hard surface. We don't want that. So here's where we work with the National Center for Supercomputing Applications in Champaign-Urbana, Illinois. And they got the computers. Hey, Alberto, how you doing? And they've got the computers to be able to take this and add the gas to it. So we added a particle layer to make it fuzzy and gaseous on top of it. All right, then we add back in the stars, and then the proplyds and the bow shocks, as well as the background stars. Because one thing you might have noticed about that previous Orion visualization is that when you're inside the nebula, that's all there was. There wasn't anything outside of it. Here, we have the full, complete Milky Way galaxy outside of it. So putting that together, and then the final piece was this idea of planetary systems in formation. And so this is Hubble's image of a protoplanetary disk. It's like 12 pixels across. Well, that's not going to do for an IMAX film, 12 pixels. So I had a friend at Jet Propulsion Laboratory, and he had done this visualization for a totally different purpose. And I said, Robert, we got to have this for the film. He was able to work it. We were able to pull it into the film as the final piece. So once again, I got to take my microphone off. I hope this plays smoothly. This is an excerpt from the IMAX film Hubble 3D.
There are amazing things happening inside these clouds.
All right, I'm going to stop this. PowerPoint is not operating nicely. I should have rebooted my computer before this. So hold on. I'm going to play this for you outside of PowerPoint. Just I can't have the highlight of my talk come up poorly. Nope, let's just go into VLC. I'm sorry, my laptop seems to be doing things that played this absolutely perfectly on Tuesday night. Okay, there we go.
There are amazing things happening inside these clouds. As we look
Okay, so here are the folks, the scientific team that worked on this, the visualization folks at Space Telescope, visual space folks at NCSA, and all of the astronomers who contributed imagery to it. And you might think that that's an awful lot of work, the months we put in for something for an IMAX film to try and keep it scientifically accurate when it's entertainment and the audience isn't really going to know anyways. But they do appreciate it, and it's not just the science geeks that appreciate it. It was Variety magazine, the Hollywood newspaper itself, that said, most mesmerizing of all are the photographs taken by Hubble itself, expertly enhanced through computer visualization techniques applied by the Space Telescope Science Institute in Baltimore. Consequently, Hubble 3D comes as close to as any film to reproducing the curious cosmic sensation of floating through outer space. Now that's a review. All right, so let's talk about this truth and beauty in science and art thing. All right, when we look at it, academia, well, we're trying to come up with a presentation of our science. We're illustrating our points. We're using very simplistic, visualization techniques, but we've got very complex physics in it. We're trying to be very exacting of it. It's more left-brained, all working towards the accuracy. Well, on the other hand, Hollywood, and they're trying to entertain you, and they're trying to tell you a story. So they don't need all the physics, but they need to have all the beautiful lighting and the geometry and the camera and the compositing. They're trying to make it look good. And that's not a criticism of them. That's what their job is. Their job is to make entertainment. And you think of them as more emotional and right brain. And I like to think of it as, accuracy and aesthetics. But what I really want is the combination of the accuracy and the aesthetics. And you might ask yourself, why is an astrophysicist lecturing me about truth and beauty? Well, I may be an astrophysicist, but as a young man, this is what I looked like. I started out tap dancing when I was 10. I've done ballet, jazz, and ballroom, and modern, and all sorts of dance. I was a competitive ice dancer. I took 3 years off after high school competing in ice dancing. I was ranked 10th in the United States back in '83 or '84. I can't remember which at this point. So I've always had a very geek side to me as well as an artistic side to me. All right, I want to be able to pull them together. And astronomy visualization really speaks to me because I can take you to that Orion sequence that I showed that we started out with. We can pull you in. We can show you the science data. We can show you this Horsehead Nebula as it appears in visible light. We can then cross-fade that visible light, this dark nebula, in infrared light turns into a gorgeous gaseous landscape. And then we can 3D-ize that image, pull it out, stretch it out into scientifically reasonable 3D, and take you in to float you in there. And it's not that this is Hubble data, which it is, and it's not that this is a beautiful image, which it also is, but it's the combination of the accuracy and the aesthetics. It is my mantra in what we are doing that the fact that there is truth behind that beauty is what gives it its true power. And that's what we try to do at the Office of Public Outreach. Thank you for listening tonight. All right, let's see, what time is it? A little after 8. Keely said we can have a few more minutes, a bunch of minutes for questions. If you have questions, please raise your hand and let me know. Yes?
In that intro photo of the scientists, it looked like they were holding a liquid film.
Yes.
Is that,
I forgot to mention, so the question was, in one of the early photos, we're holding a piece of film, right? That piece of film is a piece of IMAX film. IMAX is it takes 35 millimeter, a 70 millimeter film and actually goes it sideways so that you get a really wide, as many pixels as possible into the image.
But the images you're getting from Hubble
The images from Hubble do not come down on film. No, no. That is another misconception we have to fight at Space Telescope, that we don't send astronauts up there to change out the film and bring it down, then expose it. Everything from Hubble has been digital since day one. Actually, astronomers have been using digital pictures since the late 1980s. Well before you guys had digital cameras on your phones and everything, astronomers were moving to charge coupled devices, CCDs, in our astronomical observatories. Other questions? All right, thank you all for coming. Bonnie, where is the get-together?
Yeah, so after this, we're headed to the Crown and Anchor Pub, just down the road a little ways, about a block. We'll all walk over together if you guys want to come with us.
And
we're
in the
going to have a few chats about astronomy, about Space Telescope, about Hubble, James Webb Space Telescope, whatever you guys want. Come with your questions, come with your discussion.
And in the back of the room, the gentleman who I said hi to in the middle of the talk, Alberto Conti from Northrop Grumman, as well as sitting next to him, Amber Strawn from Goddard Space Flight Center. They are both experts on the upcoming James Webb Space Telescope. You think these infrared images are pretty from Hubble? Just wait till 2018 when JWST gets launched, and it'll produce even greater and cooler and amazing images in the infrared. And Amber will talk your ear off about it. She has some amazing things to say. Anybody else going to be at the thing that I need to mention? I can't see everybody back there. Is that you, Christina? Yes, I see Christina. Hi, Christina. All right. All right. Anything else we should say about that?
Yeah, well, we should also say that if you would like to see more of Frank's visualizations, we have a gallery now at Hubble site. We have a QR code here if you just want to scan it. HubbleSite.org/videos. And we have a new beautiful gallery you can search through. There's many more visualizations and videos than even the ones that Frank just showed.
And not everyone that I showed is on the album gallery yet. We're processing them a few at a time. So we've got about 12 of them up there now, and we'll be putting new ones up every other week probably for the next several months until we are fully populated. So cool videos. Please come take a look. All right.
And we're at South by Southwest the next 3 days doing the Gaming Expo. So it's free and open to the public. Come see us, check us out. We have this really cool quarter of what the James Webb Space Telescope mirror will look like, but it has mirrors on the sides of it so that it looks like you can see the whole thing, because it'll be huge when it's deployed in space. It'll be over 21 feet wide. So you can stand there, like feels like you're sitting next to this huge segmented mirror telescope. Have your picture there. Frank will also be there with some of these visualizations on a huge display screen that you can touch. So come on out and see us.
Right in front of you, okay? We've got the amazing images from Hubble of planets and of stars and of nebulae. Amazing views here. We've got galaxies. And the images from the Hubble Space Telescope, using them, we can start with the visual beauty of the universe and use that to sort of lead you in to the scientific truth. And so that's what we do in the Office of Public Outreach. We're able to take the amazing images from Hubble and bring it out and teach the public about astronomy, using them as a drawing in card to then get you into the science. So I'm going to tell you a few stories tonight. And I have to thank my collaborators, Greg Bacon, Lisa Furtari, and Zolt LeVay. These are my three main collaborators on a lot of the work you're going to see tonight, as well as Tiffany Davis up here, who's no longer with us at Space Telescope. She's still alive. She helped us on some of our projects here, okay? All right, 4 stories for you. I got so much to tell you. I'm going to have to really zoom through it, but here we go. First, we're going to start with Night of 1,000 Stars. So when you look up at the night sky, well, you can see lots of stars. You really can see thousands of stars. Actually, across the entire celestial sphere, the human eye can see about 6,000 stars. Now, people might recognize the familiar pattern on here. Who knows what that is? Just shout it out. Orion. Thank you very much. Got to make sure that everybody catches that. And this bright star down here is Sirius. And up here we have the Pleiades of Odon and Grecian Urn. And it's really the last 2 lines. where the urn is saying, "To whom thou sayest, beauty is truth, truth beauty, that is all ye know on earth, and all ye need to know." Now, that is a line that equivalences truth and beauty and puts it up on such a pedestal. And the public actually became very enamored of it. They liked this idea that truth and beauty could somehow be equivalent. Of course, if the public likes it, you know that the critics are going to hate it. So, Josiah Condor in the Eclectic Review said, "That is all that Mr. Keats knows or cares to know, but till he knows much more than this, he will never write verses fit to live." Of course, Keats' verses, especially the lines he's criticizing, did live, and the only thing that I've ever heard of Josiah Condor, of his words that lived, were his criticism of Keats. However, T.S. Eliot said, "On rereading the whole ode, this line strikes me as a serious blemish on a beautiful poem. And the reason must be either that I fail to understand it, or that it is a statement which is untrue." And when you've been dissed by T.S. Eliot, you've been seriously dissed, right? Well, I'm not an English major, and this line has never really bothered me because this is a line where the urn is supposed to be speaking to man and saying that beauty is the highest goal. And the urn is a piece of art. And on Earth and keeping it in orbit around the sun, instead the space-time around the sun is curved and warped, and that curvature and warp produces the orbit of Earth around the sun. And all of that wonderful idea of space-time curvature can be expressed by a mathematical equation, a tensor equation, given here. And it is very symmetric. It's symmetric in space and time. All right, these Greek subscripts here, mu and nu, actually cover both the space part of it and the time part of it. And to be able to take space and time and work them together is a very beautiful symmetry. However, I will be honest with you that the Ricci tensor here is actually defined in terms of partial differential of something called the Christoffel symbol. And the Christoffel symbol is also defined as partial differential equations of the metric tensor components. And so, actually, we usually called the Christoffel symbols in graduate school the Christ-awful symbols, because when you had to try and solve these equations, it was really an awful lot of work. So I must say, at least for me, getting into the really depth of the mathematics here removes some of the beauty from general relativity, but I can still appreciate its wonderful, the wonderful symmetry that it has. Now, I'm from the Space Telescope Science Institute. We're the science home of the Hubble Space Telescope. So we got it easy. We don't have to start with truth and try to lead you into understanding the beauty of these equations. We got the beauty part. Attaining beauty is your highest goal, so beauty can be your truth. All right, and your truth can be beauty when you are thinking in art. So it's never really bothered me. Of course, I'm a scientist. And in science, we're trying to get at the truth, or at least a good approximation thereof. And we also have an idea of scientific beauty. This is the Institute for Advanced Study in Princeton, New Jersey. Very famous think place for deep thinkers. And the IAS medal actually pulls from Keats and has truth and beauty. Or when I was in Princeton, we called them Ruth and Betty. And you can see that the IAS is dedicated to uncovering the naked truth. Now, they specifically quote Keats when they're presenting this because scientists are in their quest for truth, really do see beauty. And the example I'm going to give you is the most famous resident of a person who worked at the Institute for Advanced Study, Albert Einstein. When he came over to America, the IAS in Princeton is where he did his research. And Einstein's theory of general relativity, which he's writing on the blackboard here, the fundamental equation of that is that the Ricci tensor is equal to 0. You set the Ricci tensor equal to 0, and you can get out the equations of general relativity. And this is an amazingly beautiful theory, okay? Because it takes the forces of Newton's gravity and replaces them with space-time curvature. So instead of a force pulling.
Welcome everybody. This is Truth and Beauty in Scientific Visualizations. We have with us tonight Dr. Frank Summers. He got his PhD from the University of California at Berkeley, after which he went to the American Museum of Natural History and did a stint there and did some cool stuff with the likes of Neil deGrasse Tyson and the Hayden Planetarium there. And then 13 years ago, he graced the Space Telescope Science Institute with his presence, where he's been in the Office of Public Outreach as an astronomer, an astrophysicist, and one of his specializations is doing these fantastic scientific visualizations. So he will tell you a little bit more about the truth and beauty parts of that and what has inspired him to create these during his talk. So enjoy.
All right. Can we get the lights down? Is Keely here?
Yeah, I'll go with it.
Hey Keely, can we get the lights up? There we go. Beautiful.
Is that too much?
No, that's beautiful because we do astronomy and we have a lot of black, so we got to have the lights down in the room in order to really work. All right, so thank you very much, Bonnie. Bonnie is another astronomer in the Office of Public Outreach at the Space Telescope Science Institute in Baltimore. And as you might guess, the title of my talk reflects the most famous lines from this gentleman, John Keats, who I found out lived only to be 25 years old. All right? But when he was age 22, he wrote his most famous poem, which was Ode on a Grecian Urn. And I have here just the last stanza